So this is the first of really 4 videos on the Diels-Alder reaction. So as a way of introduction, I wanted to mention pericyclic reactions. So most organic reactions, and certainly most of the reactions that we've seen so far, both this semester and last, occur through either an ionic or radical intermediates. Pericyclic reactions, however, are a class of reactions that do not. And there are 3 main types of pericyclic reactions. There are cycloadditions, and the Diels-Alder reaction is an example of a cycloaddition, and so this is the type of reaction that we're going to be focused on through these next several videos. We also have electrocyclic reactions and sigmatropic rearrangements. Now, just from this slide, you can immediately see some similarities, right? They all seem to involve rings. They all involve concerted movement of electrons in the mechanism. So just jumping into those similarities a little bit more, for all of the pericyclic reactions, the mechanism is concerted. And we saw that with the movement of all those electrons simultaneously. And so this means that they generally proceed without any intermediates. So just a single transition state separating the reactants from the products. We saw on the last slide, the mechanism involves a ring of electrons moving around a closed loop. For all of these reactions, the transition state is cyclic. And because they don't involve ionic intermediates, the polarity of the solvent is generally not a big factor in the reaction rate. Okay, so let's start jumping into the Diels-Alder reaction specifically. And so this probably looks familiar to the previous slide. A Diels-Alder is an example of a cycloaddition. So when we combine these 2 molecules, we end up forming a ring. Now, a Diels-Alder reaction is an example of a 4+2 cycloaddition. And what those numbers refer to, in the compound on the left here, we have 4 carbon atoms involved in a conjugated pi system, and then we have 2 carbon atoms in the compound on the right involved in a pi system. So that's where the 4+2 comes from. It's telling about how many carbon atoms are involved in the pi system in each of the molecules. Now, we saw this mechanism before, and like all pericyclic reactions, the mechanism is concerted. So all of these electron movements take place at the same time. And so we form 2 new sigma bonds, and then this pi bond just moves over 1. All right, when we mentioned because this mechanism is concerted, and so it all takes place in a single step, we have a cyclic transition state that we talked about, and then it's just a single 1-step reaction to convert the reactants into the products. So most Diels-Alder reactions are thermodynamically favored at low and moderate temperatures. When we get to much higher temperatures, talking like 200 degrees Celsius, the reverse reaction, or the retro Diels-Alder reaction, can predominate. And so at low temperatures, it's the stability of the products that dominates whether reactants or products are favored. And at high temperatures, it's the entropy that starts to dominate. We're going to spend the next couple slides talking more about that. But we can see on this slide, right, at low temperatures, we get the ring-forming reaction. At higher temperatures, we get the ring decomposition reaction, the retro Diels-Alder. So to understand whether reactants or products are favored, we have to consider free energy, or delta G. And hopefully this equation is familiar to you. We've used it quite a bit in both 1212 and Orgo 1. The free energy depends on both the enthalpy and the entropy of the reaction. The enthalpy, of course, is related to the heat of the reaction, and the entropy is loosely related to the disorder. So if we first think about what the sign on delta G is going to be for a Diels-Alder reaction, if we look at what bonds we're making and what bonds we're breaking, on the reactant side, the bonds that we're breaking 3 pi bonds. And then the bonds that we're making when we form the products is we're forming 2 new sigma bonds and then a new pi bond. And generally, pi bonds are weaker than sigma bonds. And so the fact that we're breaking more weaker bonds and we're making more stronger bonds means that the delta H for this process is going to tend to be negative, right? Delta H is less than 0, or delta H is negative, because we're going from something that has weaker bonds, so it's less stable, to something that has stronger bonds, so that it's more stable. So a more stable product means that the reaction is going to give off heat. The reaction is going to be exothermic, or again, delta H is going to be negative for this process. Now, when we consider the entropy term, when we go from two reactants to a single reactance, this is always associated with a decrease in a disorder, or a negative delta S. So for the Diels-Alder reaction, moving in the forward direction, we expect both delta H and delta S to be negative. All right, so let's kind of put it all together. So we said delta H is going to be negative, and delta S is going to be negative. But in the equation, delta G is equal to delta H minus T delta S, we also have to consider the negative T, right? So when we take negative T and multiply it by a negative delta S, that means this term, this entropy term, is going to be positive. Now remember, for a reaction to be spontaneous, we want delta G to be negative. We want delta to be less than 0 to be spontaneous. And so if we consider what happens at low temperatures, right? So the easiest thing to do when we think about low temperatures, let's just go as low as possible, right? The temperature has to be in Kelvin, so let's make the temperature 0. So at low temperatures, we can essentially ignore the entropy term, and the enthalpy term is going to dominate at low temperatures. And because the enthalpy is negative, that means at low temperatures, delta G is going to be negative, and it's going to be spontaneous, meaning it's going to be product favored. Right? On the other hand, at very high temperatures, right, we can make T as big as we want, make it infinity if we want, right? That means at high temperatures, the entropy term is going to dominate, right? And because the entropy term is positive, that means at high temperatures, delta G is going to be positive. So the reaction will be spontaneous at low temperatures where the enthalpy term dominates, meaning it's going to be product favored. And at high temperatures, the entropy term is going to dominate, meaning delta G is going to be positive, so it's not going to be spontaneous, and the reactants are going to be favored. Okay, so a couple more notes on the Diels-Alder reaction. So we've talked about the temperature dependence on the previous slides. This first bit is just a note of terminology. So the compound on the left here is a diene, and so when we talk about the Diels-Alder reaction, we often refer to this being the diene, and then the alkene, the other alkene that's not a diene, they often call that the dienophile, right? It is attracted to the diene, so we call it the dienophile. And so this is the terms that we use to distinguish these two different reagents in the Diels-Alder reaction. Now, a note about the dienophile, right? This guy. If we just have ethene, the reaction needs high temperatures in order to proceed. And we just talked about the fact that high temperatures don't favor the reaction. So when we get it hot enough for this reaction to actually proceed, the product yield is relatively low. So what can we do to the dienophile to make the reaction more favorable? Well, if we add an electron withdrawing group, we can make the reaction proceed at lower temperatures. All right, so in the last slide, we just had ethene, and we had to heat it up a lot, and we got very little product yield. Well, if we put an electron withdrawing group, in this case an aldehyde, onto the dienophile, we can actually get very good yields even at lower things, closer to room temperature. And some other examples of electron withdrawing groups are given down here. So ketones, in addition to aldehydes, esters, carboxylic acids, and cyanide groups all act as electron withdrawing groups. Now, why are they electron withdrawing groups? Well, let's take a look at the resonance structures for this aldehyde here. So if I think about the possible resonance structures, the first thing I can do in terms of drawing resonance structures, I can move that pi bond up to be a lone pair on the oxygen. That makes the oxygen negative, and then the carbon that lost the pi bond becomes positive. Well, now I have an allylic carbocation, so I can draw another resonance structure like that. Right, and so this resonance structure down here, we end up with a positive charge on one of the carbons that was involved in the alkene that's involved in the reaction. So by making the alkene more positive, we've withdrawn electrons, and so that's why we refer to these as an electron withdrawing group. And you'll see that all of these groups have sort of the same thing in common, right? We've got a pi bond connected to a more electronegative atom than carbon, so I can do that first resonance structure where I move the pi bond up to the oxygen, and then I'll have an allylic carbocation. Same thing here, and then cyanide, is C triple bond N, so I can do the same thing. And then I can always draw that second resonance structure where I have the allylic carbocation. And so all of these groups act as electron withdrawing groups for the same resonance argument as we had for the aldehyde here. Okay, so this is the last slide on this video, but then we'll pick up and look at more specifics about the Diels-Alder reaction in the next video. I want to mention that the Diels-Alder reactions are stereospecific. And what we mean by that, if we have a cis dienophile, we'll have a cis cyclohexene in the products. If we have a trans dienophile, we'll have a trans cyclohexene in the products. And the final thing I want to mention, not only can alkenes serve as dienophiles, so can an alkyne. In that case, we just end up with an extra double bond as part of our cyclic ring. And then because these are sp2 hybridized carbons, we don't have to worry about showing any stereochemistry because, of course, these carbons are going to be planar.